Welcome to the Explainer. Today we're diving into some massive AI news that's tackling one of the trickiest infrastructure problems out there, bringing heavy computer vision out of the cloud and straight onto low-power devices. We are unpacking a brand new arXiv paper, specifically 2606-12473. It details an incredibly clever, privacy-preserving fall detection pipeline running entirely on the edge, powered by quantized YOLOX, A2J pose estimation, and a CNN classifier, all humming along on an AMD Kria K26 device. Let's get into it.
So, think about the ultimate health tech paradox. How do we protect vulnerable patients without sticking a camera in their living room and destroying their dignity? It's a really tough balance. On one hand, over 3 million older adults end up in the ER for fall injuries every single year, meaning we desperately need real-time detection. But on the other hand, streaming a live video feed of someone's private home to a remote cloud server, that is a massive privacy violation. So how exactly do we bridge that gap?
Well, here is our roadmap for today's Explainer. To answer that, 1. The healthcare monitoring problem. 2. Edge architecture and hardware. 3. The three-stage AI pipeline. 4. Privacy by design. 5. Performance and hardware metrics. And 6. Next steps for developers.
All right, Section 1, the healthcare monitoring problem. To really grasp why this paper is such a big deal, we have to look at the baseline we're trying to fix.
Look at the friction we're currently dealing with. Wearables are plagued by battery drain and what we call compliance fatigue. People just forget or don't want to wear them. Meanwhile, cloud-based cameras eat up bandwidth, introduce network latency, and are huge privacy liabilities. That is exactly why this paper shifts the entire workload to a battery-operated, edge-based system. We get on-device processing that is inherently privacy-preserving.
Moving on to Section 2, Edge Architecture and Hardware. Let's look at the actual silicon, because you can't run a complex vision pipeline in a living room without the right hardware.
The researchers kick things off with the Intel RealSense D455 camera. And you guys, this is not your everyday webcam. It's capturing 640 by 480 resolution at a super crisp 60 frames per second. It's packed with global shutter depth sensors and a built-in IMU. But the real magic? The RGB color video and the infrared depth data are perfectly synchronized frame by frame.
And where does all that rich, synchronized data go? It's fed via USB straight into the compute backbone, the AMD Kria K26 system-on-module. This proves you can absolutely do heavy compute on low-power, battery-operated edge silicon. The K26 has a dedicated deep learning processor unit, or DPU, which lets it chew through 60 frames a second of raw data locally. Zero cloud connection required.
Which brings us to Section 3, the three-stage AI pipeline. Instead of throwing one giant, clunky neural network at the problem, they got smart and modular.
Here is the absolute heart of the Explainer. It's a three-step flow: identifying the human, mapping out their skeleton, and then classifying their trajectory. We're talking YOLOX for detection, A2J for pose estimation, and a CNN for classification. Let's break down exactly how this data flows from one stage to the next.
Stage 1. We've got a quantized YOLOX model, which was trained on the crowd-human dataset, working the RGB stream. Its only job is to look at the color frame and draw a bounding box strictly around the human. It's pure localization. We just want to find the person so the system doesn't waste precious compute cycles analyzing the living room sofa. Then, Stage 2 hits. And this is cool. The system completely switches gears to the depth stream. It uses an anchor-to-joint, or A2J model, to process those depth frames. It takes the bounding box from Stage 1 and maps out 15 specific 3D joint key points, like shoulders, elbows, and knees. It's basically building a digital, three-dimensional skeleton in real time. Finally, Stage 3, a convolutional neural network steps in to make the big decision: fall or non-fall. But here's the kicker. It isn't looking at pictures. It's looking at pure numerical data. It analyzes the X, Y, and Z coordinates of those 15 skeletal key points over a sequence of frames, recognizing the distinct physical trajectory of someone falling versus just sitting down quickly.
Section 4, Privacy by Design. This is an absolutely critical architectural choice if you want to get this tech compliant with strict healthcare regulations. Here is the genius of privacy by design. By intentionally dumping the RGB color data immediately after YOLOX draws the bounding box in Stage 1, the system physically cannot leak facial identifiers or room details.
Stages 2 and 3 run exclusively on depth data and numbers. There's literally no video left to hack. It's mathematically incapable of exposing the patient's identity, effortlessly ensuring HIPAA and GDPR compliance.
Okay, let's talk numbers in Section 5, performance and hardware metrics. A brilliant pipeline is great, but how does it actually run on the silicon?
As you can see, the quantized models hold their ground. Remember, they had to be compressed to fit on the Kria K26, but YOLOX still hit 74% accuracy. The A2J pose estimation achieved over 84% accuracy within a 10-centimeter margin of error, and the CNN classification sits right around 75.85%. Sure, 75% means we have some optimizing to do before we deploy to a hospital ward, but as a proof of concept, it's phenomenal. Now, when we look at pipeline latency and throughput, we see a massive difference depending on exactly how that DPU is utilized. Running 3 models sequentially eats up a lot of time.
But by splitting YOLOX and A2J across a dual-core DPU using multi-threading, the team pushed the throughput from a sluggish 2.5 all the way up to 4.5 frames per second. That jump from serial to multi-threaded execution is huge, because 4.5 frames per second makes near real-time detection genuinely feasible.
Section 6, next steps for developers. If you're an engineer watching this explainer and building edge vision systems, you need to take notes here. These are your crucial takeaways. First, INT8 or FB16 quantization is non-negotiable. If you try running uncompressed models, your frame rate will completely stall the DPU. Second, multi-threading is great, but it introduces race conditions. You have to explicitly manage your double buffering so your depth frames perfectly synchronized with the RGB frames that generated the bounding boxes. And lastly, remember that public datasets skew heavily toward highly controlled environments.
Which brings us to production readiness. That 24% error rate we saw earlier, it means you will get false positives in a messy, real-world home. To fix this, deployments are going to require temporal windowing, like demanding a fall is detected across 3 consecutive frames before sounding an alarm. Or, even better, utilizing IMU sensor fusion from that Intel RealSense camera to confirm sudden drops in velocity.
Which leaves us with this final massive question. As edge silicon like the Kria K26 continues to get faster, are wearable medical monitors about to become completely obsolete? If we can process complex 3D skeletal data locally in real time with zero privacy risks, maybe we can finally say goodbye to those uncomfortable lanyards once and for all. It's a wildly exciting future. Thanks for joining me for this explainer, and keep building.